Hello and welcome back. This is Mr. Wakefield again, and we're looking at section 7.4 right now. And in particular, I want to look at going beyond what we talked about before in the previous couple of sections. We talked about right at the end of 7.3, we were talking about radical terms and multiplying those radical terms. Remember, when we have a radical term, that means that you have a radical times a regular term in front of it. So like this right here, that's a radical term right there, okay? Sometimes it doesn't have anything in front of it. That would still be a radical term. It would just be an invisible 1 in front of it when that happens, all right? But this has a 5 in front of it, so that's a radical term also. This also is a radical term because, again, you have a radical 5, times a regular term 3. As we talked about at the end of last section, when we have that right there, we can multiply what? We can multiply 5 times 3. In other words, we can multiply the outside parts. The outside times the outside stays outside. It doesn't go into the radical. And then the inside times the inside of the radical, 7 times 5. Inside times inside stays inside. Okay? And so that's how it works when you multiply a radical term times another radical term. Outside times outside stays outside. Inside times inside stays inside. Okay? But what I wanted to particularly point out here in this section is that just like when we multiply regular terms together, it doesn't matter if they're like terms or not. Nothing needs to be the same like it is when you add and subtract terms, right? When you add and subtract terms, the only way I could add or subtract them together is if they are like terms. And since these are like terms, I could add or subtract them together. But if I had something like this, okay, something like that, I wouldn't be able to add those together, would I? Okay, I just have to stop right there and say I can't do anything, all right? But when you're multiplying terms together, nothing needs to be the same, just like with radical terms. Radical terms, the radicals don't need to be the same. The numbers in front of the radicals don't need to be the same either. Okay, you can multiply any two radical terms together, just like you can multiply any two regular terms together. 15x to the 6th. Okay, for example. Well, radicals are the same way as regular terms when it comes to adding and subtracting also. Okay, when you're adding and subtracting regular terms, they've got to be like terms. In other words, the variable part of the term has to be the same, doesn't it? X squared and x squared, for example, right here. Well, it works the same way with radical terms, all right? When you're adding or subtracting radical terms, the only way that you could combine them together, just like you combine like terms, the only way you can combine these terms together is if something's the same here as well. What is that something that needs to be the same? It is the radical. The outside of the radical doesn't need to be the same, just like the coefficients didn't need to be the same over here, but the radical does. And so, since these are the same radical, not only can we combine them together just like we combine these together over here, but we combine it in a very similar way. What you do is you add the 5 and the 3 together just like you did here. All right, you get 8 radical 6. And notice the radical 6 stayed the same, just like the x squared stayed the same. Remember, when you combine like terms, the variable part of the terms has to be the same, and then it stays the same when you combine it. Same thing with radicals. They have to be the same, and then they stay the same when you combine. All right? Same thing with subtraction. The radical has to be the same, but then if it is, then you just do 5 minus 3 right there. You combine the terms in front of the radicals, and then the radical itself stays the same. Okay, one big difference, though, between adding and subtracting regular terms versus adding and subtracting radical terms is that if you do have two terms that are not like terms when you're adding regular terms or subtracting them too, you just can't do anything. But the difference is that when you are adding and subtracting, say, see how we got 3 radical terms here, you guys, that we're adding and subtracting? Yes, it's true that they don't have the same radical. But that doesn't mean that we can't make the radicals the same by simplifying them, okay? And notice down here that that's exactly what I did. Pardon all this work here, okay? I didn't set it up as in such a way that it's very easy to read. But just trust me, and I'll show you how I did it here in some problems down here at the bottom of the page. But eventually, after I simplified the radicals, this is what the problem ended up looking like right here. And again, you'll see how I get from here to here as we go through the problems here today. But now that I am at that point right there, since all of these are the same radical, I am allowed to do 8 plus 6 minus 4, which is equal to 10. And so that's why the final answer is 10 with the radicals staying the same. It's all because we're adding and subtracting these radical terms. If we were multiplying them, that'd be a different story. That's where that thing comes into play up here, where you do the outside times the outside and the inside times the inside. But because we're adding and subtracting these 3 radical terms here, okay, you can see we still have 3 radical terms here. This one, and this one, okay? Since they all have the same radical, you can combine them. So let's try it out, okay? Notice here we're adding together 2 radical terms. There's an invisible 1 in front of this radical 75 right here. They're not the same radical, no doubt about that. But as I just mentioned, just because the radical is not the same doesn't mean that we can't at least try to make it the same. I'm not promising it's always going to become the same when you simplify it, but it usually will, at least in this section it will, okay? And there's a reason why they say add or subtract is indicated. It's because we will be able to do just that. All right, so they're kind of hinting at the fact that, yeah, you're going to be able to make these radicals the same. All right. So let's simplify these. As we learned in the last section, all right, I can pull out what here? Okay, 1 and 4 would work for 12 as far as the perfect square numbers that we can factor out of that. But 4 is the biggest one that works, right? Okay, so I can factor the 4 out. Again, there's just a little review of what we did last section. 1 and 4 will work, but 4 is the biggest one that will work there. 4 times 3 is 12, so 3 must be the other radical there. And this becomes what? This becomes 2, radical 3. Remember, evaluate the first radical, keep the second one the same. For 75, 1 will always work, but is there something bigger that works? 4 does not work for 75. 9 doesn't either. 16 actually does not either, but 25 does. Is 25 the biggest one that works? Let's find out. The next one would be 36. That doesn't work. Again, use your calculator to help you. The next one is 49. That won't work either. And then the next one is 64. No, that's not going to work either. None of those divide evenly into 75. But then the next one after that is 81, and that is too big, along with everything else after that on the list of the perfect squares. So 25 must be the correct one. All right, and so if we then do what we normally do here, which is to evaluate the first radical and keep the second one the same, we get 5 rad 3. All right, what's cool about this now is that both of those radicals now are the same, aren't they? Okay, and so I can now carefully now, let's be careful about this. I can now take these 2 new answers down here and go back and replace the old radicals with those new answers. Now remember, the 5 is separate from those radicals, so along with the plus sign. And so the 5 and the plus need to stay the same. I mean, they didn't get replaced. It's the 2 radicals, the 2 original radicals that got replaced. So I'm going to take the original radical and I'm going to replace it with 2 rad 3. And I'm going to take the second original radical, there 75, I'm going to replace that with 5 rad 3. All right, now don't add together yet. I know the radicals are the same, but don't add together yet. And the reason why is because if you had a term in front of one of your radicals, which we did here with 5, we didn't over here, but we do here, okay, we need to multiply that 5 by our new thing that we plugged in behind it there, okay? And we learned in the last section about how to do that. We learned that one of the last problems we looked at, we learned that 15 squared of 90 transformed itself. In other words, we simplified the radical 90, just like we simplified the radical 12 just a moment ago, and we're going to look at it again here in just a second. But rad 90 simplified into 3 rad 10. So what did we do when there was a 15 that was already in front of that simplified radical? We then multiplied the 15 times the 3. Remember, you're allowed to do outside times outside. Don't ever do outside times inside, ever. Okay, but we can do outside times outside. And then since there's only one radical here in this statement, okay, that's of these two things being multiplied, that would just come down into the answer. Same exact thing is going to happen here in this current problem here. Okay, we have an outside part times a radical term. You multiply, in other words, a regular term times a radical term. You multiply the outside parts, 5 times 2, just like 15 times 3. Okay, and we get what? We get 10. And then just like the rad 10 came down into the answer on that previous sheet, the rad 3 just comes down into the answer. So 10 rad 3. Again, there was no term in front of the original radical on this one, so it just stays as 5 rad 3. There's nothing that needs to be combined with that. Okay, there was nothing in front of that radical. Now it looks like something that we can actually combine now. All right. Just like I talked about earlier, if you know, and this is the reason why you had to do 5 times 2 right here. You need to know what you have in front of each radical so that if the radical terms are, or pardon me, if the radicals are the same, then you'll know what to add together, okay? So I needed to know that that was 10 first. That's why you need to multiply by the 5 there, okay, so that you know what you're going to be adding. Since the radicals are the same, and only because they're the same, if they weren't, that would be different. Then we'd be kind of stuck here unless we can simplify the radical still. But since they are the same radical, you can combine the radical terms together, and we get that as our final answer. So we did what they asked us to do. We added the radical terms together, all right? And on some problems, we'll be subtracting like the directions say, but this one was an addition problem. Let's try that again. Once again, in this problem, we have cube roots this time, though, but once again, it is true that the radicals are not the same. They're close to being the same, but they're not, okay, as you can see here. So, since you have 2 variables in each radical, no coefficient other than an invisible 1 there, but since you have the 2 variables, you need to do 2 different things here. You need to first of all look at the x, and then you look at the y. From the x, what do we got to do there? We got to pick the biggest exponent that is not too big. The biggest exponent, remember, looking at the cube list here, because this is a cube root. The biggest exponent that's not bigger than x to the 4th. That would be x to the 3rd, wouldn't it? Okay. How about for y? Well, the problem with y is that its exponent is too small for even the smallest exponent that's available to us, which would be y to the 3rd. And so we can't factor anything out of that. Okay. And so what does x to the 3rd get multiplied by in order to still equal this here? Remember, it's still got to be equal. It would be xy squared, wouldn't it? And then once I've got my 2 radicals, I then, again, evaluate the first radical, keep the second one the same, like that right there. Okay. Now look at this other radical. Isn't this other radical already simplified? Because each part there, the x and the y to the 3rd, or pardon me, the y to the 2nd, both of those exponents, x to the 1st and y to the 2nd, are too small for even the smallest exponent that we could possibly factor out, which would be x to the 3rd and y to the 3rd. So if each part is something where you can't factor anything out of it, okay, other than maybe a 1 if there was a coefficient there, that would be the only thing you could possibly do. And there's not even a coefficient there other than an invisible 1, so that doesn't matter. But when it comes to your variables, okay, if you can't factor anything out of it, And if the coefficient, whatever it may be, if the number 1 is the only factor that you can factor out of it from the list of perfect cubes, then that means that this thing's already simplified. Okay, there's nothing you can factor out of it. Okay, other than a 1, which is not going to, as I've said before, that's not going to do anything, is it? Okay, that's not going to make it smaller. The goal of simplifying the radicals is to break it down to smaller parts. Okay. So I do the same thing I did in the last problem. I take the 4 and I take the plus 5x and I keep that the same, all right? But the radicals get replaced by their new things down here. One of them won't get replaced because it didn't change. So I'll go ahead and write that down again. Again, this one doesn't get replaced because it didn't change, but the other one did. All right, and so we need to replace that. Let me write that down. And you can see now that the radicals are the same, but hold on just a minute. There's that one step we got to do first. If you had something that was outside of a radical and the radical changed, in other words, it's simplified down to something else, okay, you need to multiply the new outside part, x, times the old outside part, 4, from up here, just like I did in this problem where the new outside part, 2, got multiplied by the old outside part, 5. And so 4 times x is, of course, 4x. All right. And now that I know exactly what's in front of each radical there, okay, and since the radicals are the same, that's the most important part, I can now add the terms that are in front of each radical together. And I know I'm adding because it says plus, or this is an addition problem. Again, the radical stays the same, okay, and then you again add the 4x and 5x together, and there you go. All right, let's do one more here. Once again, our radicals are not the same. Once again, our goal is to try to make them the same. Okay, starting out with 81. Now remember, when you have a coefficient and you have a variable part of the term there, all right, you do each part separately. So for the 81, what's the largest thing from the perfect cube list that I could get out of 81? Okay, what do I got here? 1 always would work, but is there something bigger? 8. 8 is not a factor of 81, but 27 is, isn't it? Is that the biggest one, though? Well, 64 does not work for 81, and everything else is too big for 81. So we factor out 27. What about the x to the 4th part, though? Okay. We need to pick the largest exponent that's not bigger than 4. Well, that would be x to the 3rd, wouldn't it? Right there. Okay. And so what does 27x to the 3rd get multiplied by to equal 81x to the 4th? That's what would go in here. 3x. Okay. We then evaluate the first radical. 3x, if you cube it, is equal to 27x to the 3rd. So 3x then must be the cube root of 27x to the 3rd. The other radical is supposed to stay the same. Okay, evaluate the first one. The second one stays the same. That's the last step of simplifying. Okay, now for 24x, we have what here? We have the 8 factors out. That's the biggest perfect cube that you could factor out of 24. Okay. And then how about x to the 1st? Well, that's too, even the smallest exponent on the list of perfect cubes would be too big for this right here. All right, remember you got to factor out the largest exponent that is not bigger than x to the 1st. Okay, well, everything is bigger than x to the 1st on the list. All right, x to the 3rd is the smallest one, and even that's too big. So don't factor anything out of the x to the 1st. What are we left with if we just factor out 8 only? 3x, right? 8 times 3x is 24x, so 3x must be the correct choice here. We then evaluate the first radical, keep the second radical the same, and there you go for that one. Okay. All right, now, since there's nothing in front of each radical here, you don't need to worry about doing that step where you got to multiply by the new outside part. What you do is you just obviously keep the minus sign still the same here. Everything that's outside the radicals, keep it the same. And then replace the old radicals with their new simplified equivalents here, which I'm writing down right now, like that. Okay, so the radicals are the same, right? And again, there was nothing outside the original radicals that you have to multiply by like we did in the second step of each of the previous problems, all right? We can just start combining the radicals together now because the radicals are the same, and I know exactly what's in front of each term. The 3x, I'm sorry, I know exactly what's in front of each radical, 3x and the 2. Here's the problem, though. Yes, I am supposed to combine the terms in front of the radicals, but I can't combine them because 3x and 2 are not like terms. Okay? Now, we've seen this kind of thing before, all right? But we're going to do that a similar thing here as well. What we're going to do is when that happens is you factor out the radical like this. You put it behind it like this. Normally when you factor out, you would put it in front like a GCF, but we're going to put it behind it. Okay, it doesn't make any difference really in this case anyway. Usually we like to put it in the front for other reasons, but those reasons don't matter here. This is fine. Okay, but since it's being multiplied, it could theoretically go in either the front of the bracket or behind it. Okay, but just like factoring out a GCF, you factor out that radical, what would be inside of here? 3x minus 2. And the reason why it's 3x minus 2 is because those are the two things that are being multiplied by the radical. So if you can't combine these terms that are in front of the radical, what you do is you put the radical over here, put a bracket in front of it, and then just say 3x minus 2 in there. If this has been plus 2, then you'd say 3x plus 2. All right? Put those two terms, all right, in there. And that's how you do it. All right? So I'm going to let you guys try these 3 problems down here at the bottom right now. Okay? And when you're done doing that, go ahead and hit the play button, and we'll take a look at the answers. Okay, let's take a look at these answers here. First of all, in number 1, as you can see, once again, the radicals are not the same. So how do we make them the same? Let's take a look down here. I usually put my simplified radicals down here at the bottom, as you've noticed. Okay. And if I simplify both of these radicals, you can see that they become the same radical, don't they? All right. And so that's good news, all right, because when we plug it back in, it looks like we're going to be able to combine them then. All right, so let's look at that here. When I plug them back in, again, keep the 5 and the 2 the same that was in front of the original radicals. You then replace the radicals with their simplified counterparts that I found down here at the bottom. Remember, you have to you have to multiply the old outside parts by the new outside parts, 5 times 3 and 2 times 2. That gives me 15 and 4. 15 and 4. And now what does that do? That means that since the radicals are now the same, I can combine like terms. All right, combine the like radical terms. We can call them like terms because they work the same way as regular like terms. But it's all because the radicals are the same that you can call them that. Okay, so now 15 minus 4 would be 11. And so, again, the radical stays the same. All right, it is the same and it stays the same. But it has to be the same in order to add or subtract those outside parts, 15 and 4. Okay, in this case, we subtract them. So that's number 1. Number 2. Again, we have 2 radicals that are not the same. What do? We try to make them the same, right? Let's take a look at that. There we go. See down here at the bottom, they are the same now after I simplify them. Okay. They both become cube root of 3x on each one of those after I simplify. And then that means that I can now go back and I can plug back in here. There was an original outside part here, y. And so that's still there. The plus y is still there. There's nothing in front of this one, so that just becomes what it was down here at the bottom. But the plus y, you got to remember to bring that down and put the new radical term behind that there that you found. Then you do the old outside part y times the new outside part 3. It gives you 3y. Again, there wasn't an old outside part over here, so you don't have to do that over on this one. And now we have the same radical, so I can combine the 2y and the 3y together and make this into a single term, and that's what you see right there. 5y times the cube root of 3x. And lastly here, the radicals, again, are not the same, but again, if you simplify the radicals, they become the same. In fact, the second radical there is already simplified. Okay, we saw something like that earlier. And so why is that already simplified again? It's because 5, the only thing you could factor out of that is 1 from the list of perfect squares. Since this is a square root, we're looking at perfect squares. All right, so if the only thing you can factor out of the coefficient is 1, and if you can't factor anything out of the variable that you have, then that means the thing is already simplified. Because the 1 is the only thing you can factor out, and that ain't going to make it smaller. It's not going to simplify it. So let me take the thing that I did simplify, which was the first one, plug that back in, multiply by the old outside part 8 times 3x, and we get 24x here. Now remember, why does it end up being like this again? It's because usually when you have the same radical here and you're adding or subtracting, in this case we're adding, you can just make this into a single radical term, like we did over here, all right? But similar to the problem right above it, their problem C, 24x and 1 are not like terms. So since they're not like terms, we need to factor out the radical, and you can only do this thing where you factor out the radical if it's the same, all right? But if it is the same, you can factor it out, put it in the back, and then you say 24x plus 1, the two regular terms that are being multiplied by the radical, those two terms are what go inside of here. Just like in that problem right above here where it was 3x minus 2. It's now 24x plus 1. Okay, so same type of thing as problem C. Okay, so that concludes section 7.4, adding and subtracting radical terms. Let me know if you have any questions, and you have a good day.